Okay, so here we have another problem similarly in normal tangential. Notice we have a pilot that weighs 150 pounds traveling at a constant speed of 120 feet per second. They're asking us to determine the normal force he exerts on the seat of the plane when he is upside down at A. The loop has a radius of curvature of 400 feet. So let's see. So we have then the weight of the pilot, in this case 150 pounds. We have the velocity at that instant is 120 feet per second. Notice it is a constant velocity. We'll talk about that in a second. And the radius of curvature is 400 feet that he does that loop. And that is at A. Okay, so we are looking for, in this case, the normal force he exerts on his seats. So normal force the pilot exerts on the seats. Okay, so let's see over here. So we have then our free body diagram. So let's draw our free body diagram. So let's say, I'll have the guy right here, right? I'll just do a block for the person. And it's of course seating. Notice the plane is backwards, or it's upside down, it's flipped when it's flying in this case. So let me draw the seat over here as yellow. So this is his seat as he's moving. At this instant, we can then say this is the tangent direction, and over here downwards, we will have the u hat and the normal direction, down the curve. So for this one, what forces are acting on the body? So we have, of course, from here, we have mass times gravity. So that's one of the forces that we have here present. So that's mass times gravity, or the weight, right? The weight is one of those forces that is always present there. And they're asking us what is also the force exerts on the seat. So we know the seat exerts a normal force because it's standing on it, right? The seat doing a normal force, but he is also exerting the same force towards the seat. All right, he's contacting the seat, so we'll do the normal force like that, right? Because he is exerting also that same force towards the seat. Instead of the seat on the guy, we're doing the guy on the seat, so we can draw it like this, right? Going up. This is the force he is exerting on the seat. Okay, so whenever we do this run right here, we can do the summation of forces then. So summation of forces in the normal direction is equals to mass times, acceleration in the normal, which is equals to mass times velocity squared over rho. Where we're doing downwards is our positive direction. And that will mean that we will have here minus or negative the normal force plus the weight of the pilot is equals to mass times v squared divided by rho. So we know also from this that the acceleration tangential is 0 because it is a constant speed that is said there, but we do have some normal acceleration. So rearranging, we cannot cancel the masses because they're not erased here. So all we have to do is basically plug in everything. So we can solve from here. All right, that the normal force is equals to mass times v squared divided by rho plus gravity, if we factor it out, or actually minus gravity if we move it to the other side. So plugging in everything, we are going to get out of here normal force is equals to 150 pounds divided by 32.2 feet per second square. Once again, because we were given the weight, not the mass. And this is times 120 feet per second, everything square, divided by the 400 feet of the radius, minus, over here will be 32.2 feet per second square. And once you multiply everything out of here, you should be able to get your normal force, which I got to be equals to 17.7 pounds.